Hi, everybody. This is your week 5 welcome video. Right now, we're marking the halfway point in the course. So fantastic job getting to this point. We are moving right along, and I'm so excited and proud about everything you've done so far. Today, I'm going to skip the graphics of the day summary. I know you've spent time on those graphics this week, but there's a few specific things I want to do right now that we usually don't do. So one is I'm going to talk about the mid-semester feedback survey. I'm also going to summarize the work that you did in both your Thursday to Saturday lab and your Sunday to Tuesday labs last week to see if we can draw meaning and figure out why we were doing those things. So let me start by talking about the feedback survey. With any survey, we have to worry about whether there's selection bias. So there were 31 responses, right? That's about a 60% response rate. So is there a difference between the type of person, the opinions of the type of person who chose to respond versus those who didn't? Could be, right? So I'm reflecting on the responses of people who actually responded. So I'm just going to read these off to you. So there was a question about the level of the material. 87% of you thought the level of the material is about right. So that's great. There's a question about pace. 74% of you thought the pace is about right. I know this is a fast-paced course, but I'm thrilled that 3/4 of you think the pace is okay. That's great. It's supposed to feel like a term system course if you were at Wellesley already when we were doing that, right? We are trying to cover an entire course of material during a summer session, which is, I know, challenging, but you guys are doing a great job. In terms of the average number of hours per week that you're putting in, I took the numbers you typed, like if you typed, I don't know, 9 to 10, I entered 9.5, right? I turned it into a number. And both the mean and median for number of hours you're spending each week was between 11 and 12, so like 11 and a half or so. So that sounds about right? We advertised that we're aiming for about 10. So that means, the people who respond to the survey are putting in a couple extra hours. But that sounds not crazy to me. So I feel pretty good about that, but you should decide how you feel about it, right? You might be an outlier compared to that. I think it's helpful just to hear that number. That's kind of where others are. If you feel like you've been putting in too much time, there's a few suggestions I can make. One is just to do less, right? So note that there's no exams here. I'm not going to give you a grade, right? So if you are spending 3 hours at the end of your week focused on one little detail of the problem set, maybe just don't. You don't have to, right? If you're having trouble balancing this with the other things you're doing and that extra, hour that you're spending at the end is really killing you, just don't do it, right? That's fine. You can learn the material as you want, but this is definitely a program where you get out of it what you put into it. So that's one suggestion. But I guess maybe a more useful suggestion would be for you to think about when you're doing the work, right? Because it's the same number of hours no matter when you do them. And if you do the work, if you do for example, the modules or start the assignments before lab, right, then lab will be more productive, right? If you come to office hours already having figured out, where you're stuck, right, then you will get your question answered quicker, and you will move on to getting stuck at the next point. So we're going to help unstuck you again, right? I don't want you to be struggling on your own late at night by yourself, right? With some kind of coding thing. There are lots of office hours. Please take advantage of them and see if you can arrange your work time so that you spend less time kind of being stuck. Don't forget about the FAQ page. Use the lecture surveys to tell me what your questions are, so that you can get as much help as is available. Another thing to note, I can see how much time you're spending. Of course, you're spending more time on a module than the number of minutes in the video. That's expected. But if you're spending twice as much, maybe you're spending too much time contemplating the questions between each lecture survey. Maybe you don't have to do that, right? Another thing to think about is just why you're taking this course, right? So some of you are doing this because your research advisor told you to, some of you are doing it because you're interested or for fun, and some of you are doing it because it's a core course for your major or minor, right? So think about that when you're deciding kind of how you want to invest your time. If you're somebody who's finding you're spending more than the average amount of time, but you're a data science major, and this is the way you're meeting your core requirement in statistics for your data science major, I think it's appropriate for you to be spending extra time because you would be doing that during the semester as well. So think about those things as you figure out your time going forward. But again, it sounds pretty good to me. Kind of where we are in terms of average number of hours per week. So then I went through the text comments, and what I usually do with class surveys is I go through and I read every comment. So anything you wrote, I read. Anything you submit in the future, I will also read, right? I'll keep the survey open. So if you fill this in after I make this video, that's fine. I'll still read it. But I went through the text comments, and anything that was mentioned more than once, I'm going to kind of list off for you. Okay, so what do you guys like about the course? People like office hours, right? If you're not taking advantage of office hours, please start doing that. There's a lot of them. The first 20 minutes of every lab is office hours, for example. Another thing multiple people mentioned was the FAQ page. Make use of the FAQ page. Maybe make a habit of going and seeing if I've added any new questions to it whenever you sit down to work on this program. You like when we spend lab time on assignments, which is often what we do, so that's great. You guys like, or multiple people like, the 20 minutes alone without your TA in the beginning of lab, so I'm glad you're liking that. And a couple of people mentioned liking the lecture surveys as well, right? One person, I think, put it in the other column, like they thought the lecture surveys were redundant. The reason the lecture surveys are in there is to force you to actually pay attention to what was in the video, right? Because research on online learning shows, I don't think you'll be surprised that it's very easy to watch a video and then just kind of not even listen to it. So the reason there's all those questions in between is to force you to think about it a little bit. Okay, so those are things you liked. What can we do better? So I was interested to see there were several people who mentioned they'd like the labs to have a faster pace. Okay, so that's interesting, and that's something that the TAs and I will discuss. You know, I think what can happen sometimes is if it's clear that a couple people are confused about something, right, then others are waiting for those answers to be explained. And that's one of the reasons we've started to use breakout rooms during the labs, right, to try to say, okay, here are the people who are stuck on this thing, and here are the people who are not stuck, and give you a chance to work with people like you. But I hear that comment about the pacing, and we will think about that. A couple people asked if we could have office hours during the Thursday to Saturday days, right? So I did that last year, and absolutely no one ever came. Okay, so that's why I didn't do it. That said, let me look at the schedule, right? Maybe there's a way that a TA or I could cover a slot in there. So that thought pending, right? I'll see if I can do anything. But again, it was a conscious decision not to do that this year based on that being totally wasted time last year. All right, so those are the only comments that were mentioned by multiple people, but again, I read everything. There was one comment made by one person about posting the modules and surveys earlier. So first of all, I can tell that nobody's getting too far ahead because I can tell, right, when you fill in the survey. So I don't think there's anybody who's, waiting, who's like weeks ahead. I can tell that's not the case. However, note that all of the modules are posted right now. Okay. When I post a lecture survey in the course outline, that tells you that I have taken the time to go through and just make sure there's no changes, no further changes I want to make to the module, just in terms of the wording of a question or something like that, right? But there are usually very tiny, if any, edits. Okay, so if you find yourself, again, I don't think this is happening to anybody, but if you find yourself so far ahead that you're bored, go ahead and watch the next videos and just take notes on your answers to the questions somewhere. And when I post the lecture survey, which is always, by the beginning of that week, then you'll have those answers ready to go. All right, so let's see. That's that feedback from you to me. You are also, in the next couple of days, each going to get an email from me, just very short, saying something like, you are totally on track toward a certificate right now, or here are some changes you could make if you want to be totally on track. Okay, and those are the only options. So please expect that email in the next couple of days. Because again, it is good if feedback goes in both directions. Let's see here. And then also I'll send an email out. I know we have another holiday coming up, so we'll handle it the same way we handled the previous holiday. If we will run the labs as usual, unless I hear from a TA that there's one we can't run, but in general, we'll plan to run them as usual. And if you're somebody who can't make your usual time, I'll have you email Helen and we'll see what we can do. And last time we were able to accommodate people. All right, two other things I want to do though during this particular welcome video. I want to talk about the simulations you did when you were calculating the proportion of p-values less than 0.05 under a variety of conditions. And then I want to talk about the regression trees you made. So let me share my screen and we will go play in R and I will show you some summary code about those examples. Okay, so what I've done here is I've read in the data set that you guys created, the spreadsheet of p-value simulations. Okay, and so the first thing we're going to talk about is type 1 error, because that's what you guys did, right? You guys did these simulations first where the mean in each of two populations were equal, right? Like the mean in one population was equal to the mean in another population. So the null hypothesis of a t-test was true. Also, the two populations were both normal with the same variance. So actually the two populations had identical distributions. Therefore, the null hypothesis of the rank sum test, that the two distributions are equal, was also true, right? So the null hypothesis was true. And you ran a simulation that repeatedly sampled, right, two samples ran the t-test and also the rank sum test and recorded the p-value. And so what I'm showing you here are histograms of your results, okay? And you can see that in both cases, the proportion of p-values you calculated that were less than 0.05 in your simulations were right around 0.05. And that is expected. This is the result that's expected based on a video you watched in the previous week, right? And let me explain this idea just because I think it helps. I've been asked a few times to explain it again. The definition of a p-value is when the null hypothesis is true, we would see data as extreme as this p-value percent of the time. So if the p-value is 0.04, that means that when the null hypothesis is true, we'd see data like this 4% of the time. So what percent of the time would we see data like that? 4%. In other words, what percent of the time would something happen that happens 4% of the time? 4%. The p-value is defined as the probability that we'd see whatever it is, right? And so what's the chance we're going to see that thing? The p-value, right? So that's the idea here. That's why we'd expect the proportion of p-values less than 0.05 to be 0.05 when the null hypothesis is true. And so you guys, by your simulations, showed that in this case. Possibly more interesting, I'm just getting rid of the blank spaces in here, was the other part of the simulation you did where you changed the means. Okay, so in most cases, you guys left one of the means at 0 and changed the other mean to a number bigger or smaller than 0. So here's a plot of all of the responses. Okay, and this one looks just a little bit silly, right? So here is the difference in population means, right? So there was a couple that were negative, but people tried differences in population means all the way up to 10,000. Okay, now look at what happens here. As soon as the difference in population means gets pretty big, turns out as soon as it hits around 3, okay, it's arbitrarily in this case, the proportion of p-values less than 0.05 is 1. In other words, when the difference in means for the populations is large, we essentially always notice that there's a difference. So here's a graphic I made just to illustrate that idea. So here are two populations where the means are, or two samples from populations where the means are different by 30, right? Clearly, we can tell based on these two samples that the means are different, right? If you can use your human eye to say clearly these are different. In fact, they could be a lot closer together, right? It could be like here, and you'd still be able to tell that they are very clearly different, right? And one of you tried something like 10,000, right? So the one mean was at 0, the other one was at 10,000, and here we have a standard deviation of 1. So clearly, right, if you sample from populations that look like this, you're going to obtain data that suggests there's a difference. 100% of the time, you'll get a p-value less than 0.05. 100% of the time, you will reject the null because it's very obvious that the null is not true when you have means so far apart. So the question then is what happens when the means are a little closer together? And because this picture makes it impossible to see, because I like that this happened, but because we did have some people choosing very large numbers, here in this plot, I can't see what's going on, right, for a smaller range. So I'm going to zoom in. It's the same picture, but I've restricted the axes from -2 to 2. So there's some messiness, that's fine, it's because people are learning and trying things. But also I see an overall pattern here, okay? And it doesn't matter yet that some are for t-tests, some are for ranked sums, they're very similar, right? But the point here is when the difference in population means is 0, there are all those 0.05s, right around there. But as the difference in means becomes more and more different from 0, the probability that we notice the difference increases. The power is defined as the probability that we get a p-value less than 0.05 when the null is not true. The power is the probability we notice when there's really a difference. If that difference is 2 standard deviations, then we notice essentially 100% of the time. Or if the difference is -2 standard deviations, we notice essentially 100% of the time. Whereas if the difference is 1 standard deviation, right, in this case, we notice about half the time. If the difference is half a standard deviation, we would notice only 20% of the time. And that's because the further apart the populations in terms of their means, the more obvious it is that the populations have different means. If we have, as we have in some of these cases, one population has mean 0, the other one has mean 0.01, and the standard deviations are 1, those two samples look very similar, right? And so you really can't tell that actually the two samples are drawn from populations with different means, and so we don't end up noticing very often. The p-values are usually not less than 0.05. And so that's what we have here. That's the general pattern. Now, these are your simulation results. Again, there's some, things that were typed in wrong, and that's fine, but you can see the general pattern just based on your simulation results. I'm going to overlay on this plot the results of some simulations and theoretical calculations here, so you can see. So for the t-test, it's possible to do these power calculations theoretically. Okay, so what I'm overlaying the plot here, the red part, make this a little bit bigger. Hold on. I'm going to rerun it so you can actually see, because I think that would be helpful if you could see what we're doing. Okay, the red part is showing you the theoretical calculation of the power for the t-test. So clearly you did a simulation, you should get values kind of near these red dots when you're doing the t-test, and you did, right? This is on top of a lot of the pink values that I drew, but this is the pattern I'm describing, right? If the truth is that the two population means are 0, then 5% of the time we expect to get a p-value less than 0.05. But as the difference in means increases in magnitude, the probability we notice increases. And by the time, in this case, we're 2 standard deviations apart, right, we notice the difference essentially all the time. Now, I want to point out that this particular power curve, it's called, is based on the sample size we use. If you change the sample size, this curve would look different. So it's not an overall rule all the time that if you're 2 standard deviations apart in the means, then it must be the case that you have 100% power. If I change the sample size, the curve would look different. So you have to do simulations typically to see what this looks like. Or it used to be the case that statistics textbooks had pictures of power curves in the back, but we don't need those anymore because you can do what we're showing here. Okay, now those are the theoretical values for the t-test, but I did run simulations just like yours, okay, just to show you. So the filled in red dots are showing you all the simulation results for the t-test. And then I did simulation results for the rank sum test as well. So the blue is just showing you, what you guys would have obtained if you tried all the values between all the kind of increments here between -2 and 2. So what are the big picture ideas? One big picture idea is the one I keep repeating, which is the power depends on how far apart the population means actually are. You can't just say, oh, what's the power of the test, and have somebody say 0.7. You have to say, what's the power of this test to notice if the standard deviation, let me say it again to be correct. You have to say, what's the power of this test to notice if the population means are different by 1 standard deviation? And then you could say, it looks like it's about 0.55. Okay, and that would be your answer. But if you said, what's the power to notice a difference of 2 standard deviations, that would be a totally different answer, right? So the power is specific to how big of a difference you're wondering if you can detect. Now, what's the other thing we might notice here? Well, I noticed that the red dots are a little bit above the blue dots. Okay, and the reason is, what that shows is that the t-test in this case is a little bit more powerful than the rank sum test. A little bit more. Why is that true? That's true because in this particular simulation, the assumptions underlying this t-test are true, right? It is actually the case that the 2 population distributions are normal. We have independence. We did a pooled test. It's actually the case that the 2 populations have equal variance. So the assumptions that the t-test is using to inform its results are completely true. Okay, whereas the rank sum test is not making use of the fact that that the populations are normal, because it doesn't want to assume that. It's not assuming that the 2 populations have equal variances. And for this rank sum, the test is throwing away the actual data values and replacing them by their ranks. So in a case where the assumptions underlying a t-test are true, the t-test is going to be more powerful than a non-parametric test like a rank sum. However, this is just one example, but look at this plot. Not by very much, right? The difference in power between these 2 examples is really small, okay? Is really small. When I do statistical consulting at the college, so I provide statistical advice to colleagues, right, at Wellesley. Often people will say, I'll recommend a non-parametric test because I really like non-parametric tests. And people will say, oh, okay, but I've heard those have low power. Those are not as powerful. Well, the reason I'm recommending the non-parametric test is that I don't think the assumptions underlying the t-test or the parametric test are true. And if the assumptions underlying the t-test are not true, then it's not even more powerful than the rank sum test, right? So parametric tests like the t-test are more powerful than non-parametric tests if the assumptions are met, but only by a little and only if the assumptions are met. Okay, so that's what I wanted to tell you about that. Now we're going to totally switch to what you did in labs. Let me open it up here. Here we go, to what you did in labs last week. I guess I have to, sometimes Jamboards are confusing. Let me go like this. Okay, so this is what you did Sunday to Tuesday. So what we have here is a series of trees that you guys made. This is the one where there were 20 people from the ANIS data set, and you use those 20 people to try to draw a tree. What's the purpose of this exercise? Why did I make you do this? It's the same reason that I had you do by hand some of those randomization tests, right? I had you by hand verify some of the t-test output last week. The idea is that you need to have a complete understanding of what the computer is doing before you let the computer do it forevermore. Okay, so although you didn't use exactly the same algorithm as any particular tree package, by making these trees, you're seeing, okay, this is how we're going to try to build a model. These are the decisions we're making. Okay, so for this data set, here's the first group's tree, the prediction. So I figured out the predictions, right, by saying things like, hey, if we actually took, for this data set called D1, those are the first 20 observations from this ANIS data set, what is the mean of the feelings about illegal immigration among people who had feminist views greater than or equal to 50 and whose vote was either 1 or 4, right, which is the node that person number 21 would fall into in this tree. Okay, and so in this case, that prediction was 49. For the next group, it would have been 21. For the next group, sorry, wait, that doesn't make sense. It's person number 21. Sorry, for this group, it was 0. Okay. For this group, there'd be no prediction because notice here that the split is 1 versus 2, but actually person number 21 had a 4 for vote 16, right? So when you make a tree like this, you want to make sure you're including everybody. So you might do 1 versus not 1, and then maybe the next split is 2 versus anything left. Okay. There's no prediction from this group. Here the prediction was 61.7. You can see people are using different variables, which is interesting. Here the prediction was 57.5, right? They're using the Latin variable in the vote 16. Here the prediction was 79, 57.5, and this is the last one. I think this was 20. Okay, so those are different predictions. They're all over the place. What's the idea here? Well, think about what we're actually trying to do. What we're really trying to do is choose variables that are going to help us distinguish between different possible values of feelings about illegal immigration. And those are the trees that are going to be most successful, right? We haven't said yet what the true answer is. And knowing this one true answer doesn't tell you overall whether the tree is most successful, but it's an exercise, right? So we're looking for variables that seem to do a good job in this data set predicting the FT illegal values, not just in your mind, you think they do a good job, that's a good way to start, but you actually can look at the data and figure out what's correlated. So if we go to the R code, well, I ran the tree model. So when I ran the tree model on all the variables, it shows only one variable. It had fewer breaks than you guys did. Now you guys can see, I think, by making these trees that you don't have to use every single variable. Okay, and you learn from the quiz that you're submitting now that you don't, there's lots of reasons you might not use every single variable. But the tree algorithm chose to make only one break. And one of the reasons for that is that in R, the party kit package doesn't like to have nodes smaller than some cutoff. And I believe in party kit, the cutoff is either 7 or 5. So you can't really split one of these nodes further and still have nodes that are bigger than 7 or 5 or whatever the cutoff is. So this tree suggests, hey, let's just group anybody who said their feminist rating was bigger than 70 versus anybody who said 70 or below, right? And you can see actually that works really well, right? Because among people who said feminist was above 70, right, here's a box plot of how they felt about illegal immigration, and then it's a much lower set of values for those who had less positive feelings about feminists. So the prediction from this particular tree was 19.54. In other words, the person had a feeling about feminists less than 70, and so we choose the mean here. This bar is the median, the mean happens to be 19.54, and that's our prediction. What's the right answer, right? So we can calculate that here. The right answer was 30, okay? Which means that, again, it's just one person, so this is not a total check on how good our model is, but it looks to me like the best prediction was the group that had 20, right? That was the Tuesday noon group. So we can all have a virtual round of applause for the Tuesday noon group. They had a few more days to reflect before they had their lab, so I think that could be why. But they're using this feminist variable, right, which is the same one that R picked out as one that's very correlated. So that's one of the reasons that that model was successful. All right, thank you for bearing with me this long. I know this is an extra long video, but I'm going to stop there. And I'm looking forward to talking to you about all your questions this week.